Link state routing is like a group of friends who each draw a map of their own house and share it with everyone else. Instead of asking a single friend for directions, each one knows the exact layout of every road in the whole neighborhood. This gives the network a clear picture of where every router is and how they are connected, so traffic can choose the quickest path. The motivation is to avoid slow, inaccurate updates and to prevent loops, just like a complete, up-to-date map helps you find the fastest way to school without getting lost. OSPF, Open Shortest Path First, organizes a huge city into smaller districts called areas, similar to how a city is split into neighborhoods. Area 0 is the backbone, the main road that connects all neighborhoods. Inside each area, routers talk directly with each other, but only a few special routers, BRS, area border routers, pass information between areas. This hierarchy keeps the amount of map data each router has to store small, just like a child only needs a map of their own neighborhood, not the whole metropolis. A link state advertisement, LSA, is like a postcard that a router sends to tell its neighbors about the road's links it is directly connected to and the cost of using each road. When a router receives an LSA, it copies it and forwards flooding it to all its other neighbors, except the one it came from. This flooding is like shouting a piece of news, so everyone eventually hears it. Because each router stores every LSA in a database, all routers end up with the exact same picture of the network, just like everyone having the same updated map after hearing the same news. Dijkstra's SPF algorithm is the math that turns the shared map into the best routes. Imagine you start at home your router and you want to visit every house in the neighborhood. You keep a list of houses you have reached and the total distance so far. At each step you choose the house with the smallest accumulated distance, then look at its neighbors and update their distances if a shorter path is found. The formula is cost of path equals sigma link cost I for I equals 1 to n, where sigma means add up all the link costs along the path. The algorithm repeats until every router has a shortest cost value, and those values become the routing table entries. OSPF assigns a cost or metric to each link so the SPF algorithm can compare paths. The default formula is cost equals reference bandwidth divided by interface bandwidth. For example, if the reference bandwidth is 100 megabits per second and a link runs at 10 megabits per second, its cost equals 100 divided by 10 equals 10. Faster highways, higher bandwidth, get lower cost, just like a wide, smooth road is quicker than a narrow, bumpy one. Network engineers can change the reference or manually set costs to make traffic prefer certain routes, similar to painting a preferred road in bright colors. Convergence is the moment when every router's map becomes identical after a change like a road closure. OSPF uses timers to control how fast this happens. Hello timers to detect neighbors, dead timers to declare a neighbor down, and SPF timers to run the shortest path calculation. Imagine a school bell that rings every minute to tell children to check if the playground is open. If a gate closes, they wait a short dead period before assuming it's permanently closed. Then they redraw their routes. Synchronization ensures all routers start the SPF calculation at about the same time, reducing the window where some routers have old information. Route summarization is like grouping several small streets into one big avenue on a map, so you don't need to list every single street. In OSPF, an ABR can advertise a summary LSA that represents many internal routes with a single prefix, reducing the size of routing tables. Stub areas are neighborhoods that don't need outside details. They only receive a default route, go anywhere else via this door from the backbone. This keeps the routers inside the stub area simple, just like a child who only needs to know how to get to the main road, not every side street beyond it. Fast Reroute, abbreviated as FRR, is a safety net that instantly provides an alternate path if a link fails, much like a backup shortcut you already know. OSPF can pre-compute a protected tunnel, using loop-free alternates or remote line cards, so when a road suddenly closes, traffic is switched in a few milliseconds without waiting for full convergence. Traffic engineering, abbreviated as TE, extensions such as OSPF-TE add extra information like lane width, congestion level to LSAs. allowing the network to steer big trucks, high-bandwidth flows onto roads that can handle them, similar to a city planner directing trucks to highways that avoid residential streets. Security in OSPF works like a secret handshake between routers. Authentication adds a password plaintext, or MD5 hash, that each router must include in its LSAS. If a router receives an LSA without the correct handshake, it discards it, preventing strangers from sending fake maps. Integrity checks such as the MD5 hash ensure the content of the LSA has not been altered in transit, just like sealing a letter with a wax stamp that would break if someone tried to change the message. Putting OSPF into a real network is like setting up a school bus system. You first decide the area layout, then enable OSPF on each router, assign interface costs, and configure timers. Performance tuning may involve increasing the hello interval on stable links to reduce traffic, or adjusting the SPF schedule to run less often on large routers. Debugging uses commands like show IP OSPF neighbor, show IP OSPF database, and debug OSPF events to watch the postcard's LSAS being sent and to spot mismatched passwords. Think of these commands as the teacher's roll call and map checking routine to make sure every student router is present and has the right map.